Hello, everyone. Welcome. We're just going to give it a few more seconds for everyone to join and get settled in. Just a few seconds to get before we get started. Give everybody the opportunity to join us for the live session. We have a lot to talk about, so we will just give it a few more seconds, and then people can just kind of join us as we go. Okay, so hello everyone, and welcome to this new webinar organized in collaboration with Velo3D, the company that in just a few years has changed the way companies make and get their metal AM parts. This has helped to start a revolution in the adoption of AM within the new commercial aerospace segment. First, let me introduce myself. My name is Davide Scher. I am a journalist and market analyst. I am co-founder and CEO of 3D BPM, a market intelligence and media company that specializes exclusively on the additive manufacturing industry. We conduct extensive market research and we publish reports on all the core segments and all the key verticals of additive manufacturing, from energy to aerospace and related markets. We also publish 3D Printing Media Network, one of the leading news and editorial online portals, trusted by AM professionals all over the world. Today, we are here to learn what Velo3D technology can do for your aerospace parts business, from aviation to the commercial NewSpace industry. And the term NewSpace is used to define a new generation of startups and SMEs that have embraced new technologies such as additive manufacturing in particular, or that's what's of particular interest to us, in order to make space more accessible and develop new space-based commercial applications in orbit and beyond. And that's exactly the kind of companies we are here to reach out to and to present to in particular. We will look at how additive manufacturing is now playing a key role in making it possible to rapidly design, develop, and produce complex engine, rocket, and satellite parts without tools at much lower costs, which is what is enabling the new space industry to exist. One of the biggest benefits of AM is that it can be used to produce very complex geometries that help make rocket parts and systems lighter, more compact, and thus a lot less expensive, not just to build, but also to fly. Velo3D enables aerospace companies to fully access these benefits by reducing or eliminating the need of supports during the build. With support from the Velo3D team and real application cases from leading Velo3D customers in the space segment, we will learn how Velo3D's Sapphire family of metal 3D printing solutions, combined with powerful software, can help organizations around the world transition critical parts to metal AM. So after that lengthy introduction, let's meet our speakers today. William Priest, hi William, is Sales Director, UK and Nordics, where he is responsible for shaping and executing the sales strategy in this region. After completing a mechanical engineering degree at the University of Exeter, he began his career as a design engineer with Red Bull Racing. By the way, congratulations to Red Bull Racing for their recent achievements, and supported special projects with Nissan Infiniti at Nissan Technical Center Europe. He then joined the Dyson electric vehicle program as an advanced design engineer within the body engineering department, owning the design and implementation of innovative technologies. In 2020, William moved to Haita Technologies, a product design, development, and production company exploiting thermal management and lightweighting via additive manufacturing before moving to his current role at Velo3D. He is well-versed in understanding customers' technical and commercial needs and has a strong passion in delivering innovative solutions to challenging customer problems. Brian Hawkes, hi Brian, is responsible for the UK and Nordic markets. He is a chartered engineer with the Institution of Mechanical Engineers, IMechE, and has a background in aerospace and automotive design. During his time as an engineer, as a design engineer, Brian worked on many parts that have an attribute of heat transfer and fluid flow. The manufacturing methods previously utilized were conventional and traditional techniques. Now he has moved into the world of additive manufacturing, where he can see the advantages of allowing the engineer to design without compromising on these types of components. In addition to his engineering background, Brian has a qualification in project management, using these skills to run engineering development projects with large OEMs. He also managed an engineering department in an established aerospace manufacturing company in the UK. He is enthusiastic about all aspects of design and engineering and uses this passion to assist customers in their AM journey from early stage to production rate. So before we start, let me just make a couple of service announcements. The webinar is going to be recorded and you will all automatically receive a link to download it. On the right-hand side of the window, of the webinar window, you will see the presentations and other materials that the speakers have made available for you to download as we release them. We want this to be as much as possible an informative and interactive session. So we are going to be running some polls during the presentations. Please feel free and you are encouraged to participate. You are all welcome to ask questions that will be answered at the end of the discussion. Please write your questions in the chat window on the right-hand side of the screen. So without further ado, let's jump into this. We have a lot to talk about, so I'm really excited because, you know, as a media in this segment, we've seen so much happening driven by Velo3D technology. So William, I believe you have a presentation to help us kind of understand the company and the technologies that you offer.
Sure. Thanks, David. Thanks for the introduction to our team and Velo3D. Thank you for everyone joining today, whatever industry or market you're from. It's good to interact with you guys. So although there's a space focus, we can keep it quite generic as well. So Velo3D, a lot of you have probably heard the name, but not heard the story. So we're a US company, founded in 2014, about 8 years old. And we actually went public last year. So you would have seen floated on the stock exchange at the end of 2021. And what are we doing? We are doing a revolutionary new end-to-end metal additive solution. So laser powder bed fusion is the hardware which we're producing, but we're also producing the software either side of this for preprint, slicing and manipulation, and also the quality and validation end during the print and after the print, so to speak. We focus on delivering complex high-value parts, and really the focus is about non-compromise and enabling design in thermal, structural elements, enabling parts and enabling designers and manufacturers to envisage what it is they really want. So it's all about ensuring there's no compromise as we move to the manufacturing stage. We have a service and support worldwide. So part of what we do, as well as delivering machines to our customers, we actually have a contract manufacturing network globally. And part of why myself and Brian are here are expanding that network and the customers into United Kingdom and Europe, which we'll talk a little bit about later. Just to give you an idea of the size of the company, we call ourselves a startup. We're probably sub 300 global employees, with about 40 to 50 in the Europe region. We also have a technical center. We've just opened and commissioning our first machine in Augsburg in Germany, which again we'll talk about a little bit later, and I invite you to come visit where we're localizing some of the technology and some of the builds. So who do we work with? So today is a space or a new space focus, let's say, and as you might have seen in the press, the media, all over LinkedIn, we have some fairly blue chip companies when it comes to space, and previously NewSpace, from the likes of Astra to Launcher to other big companies such as Lockheed Martin Space Systems. We're delivering very quick turnkey end-to-end solutions for these guys. As well as that, we span across aerospace and defense, energy, oil and gas, and then within a few other sectors with the customers there. And within that plethora of customers, we also have some of the contract manufacturer network. So you'll notice Schürrle Bleckmann Oilfield Technology are based out of Austria, one of our European contract manufacturers. as well as the likes of DMP, for example, who have been supporting us in the US across a range of materials and a range of platforms. So these are some of the guys that we're working with. There's some very interesting synergies there, and today is the focus on NewSpace, but really when you distill the problem, the manufacturing or design problem, down to its building blocks, everyone has the same challenges. So we'll discuss that later in a bit. Brilliant. So see the polls coming in. So a mixture of markets. You're on mute, David.
I didn't want to interrupt you, but it's very interesting that you mentioned that we are here to talk about aerospace applications, but really the solutions for aerospace address every segment in additive. And in fact, many of our from our audience are from the energy, automotive, and medical segments. So and we've seen in the past how with Velo 3D technology, it's easy to address, to move to address other segments as well. So enter into new segments. So now we have 9% of our respondents from the aerospace that have a particular interest in the aerospace segment, 9% energy, 36% automotive, and 45% medical.
So moving on in detail, what are we doing? What are we providing to our customers? On the initial phase, the top image there is our Sapphire Printer, which is our first creation, really the basis of our business, and we expanded from there. And this is a 2-laser, 1 kilowatt laser system, primarily with a bed size of about 315 millimeters by 400 in Z height. But really, this was the first creation of what we call the 1MZ platform, which we actually pushed through the family as a modular system. And this was driven directly from some of the guys in the space industry, as the need to go taller in Z rather than out in X and Y as many other machine suppliers were typically doing. As we moved forward, we saw the need for the bigger bed size along with the Z height. So our latest creation, which is commercially available, is what we call the Sapphire Xc. And this is available in a 1MZ platform, which relates to the 1,000 millimeter Z height drop, which we're able to achieve. It's an 8-laser system, primarily designed around achieving bigger bed size with quality, but also improving yield and throughput. So essentially, if we want to move into a more manufacturing supply chain solution, we'll aim to utilize the Sapphire Xc. It's a inert environment, an argon environment. We can go into the specifics in more details a little bit later. And essentially what we're doing across this family is producing the same geometric capabilities with identical build parameters across the entire fleet. And some of you on the call might have heard that we have something called the golden print file, which essentially is a very high-level term of describing that we can essentially lock in our parameters, our material validation, and print on any machine in our global CM network or customer network. And this ensures we get repeatability and can ultimately produce a solid supply chain moving forward. Within the part as well, within the hardware, we talked a little bit about software, and on the back end, there are many hardware sensors giving us a lot of real-time data to make changes within the build, whether that's calibrations or simply just to know whether or not we've got a good part before we've even finished. So we've got some interesting hardware, a non-contact recoater, which some of you might be aware of, which allows us to do other things which other people can't. So that's the machine family. I'm happy to take some questions at the end about the family or even offline.
Absolutely. And we have the results from the second poll as well, with 50% of the respondents interested and that already have a metal 3D printer and are looking to install more. And 17% of the respondents that are looking for metal AM services.
Brilliant. Thanks very much, David.
Sorry, yeah, those are the main two. So, oh, and also now with 14% that are looking for metal 3D printed parts, so directly parts, and we will explain the subtle difference between a service provider and the part provider using additive. But please go ahead.
Sure, thanks, David. I think the next question is for you. You're on mute.
Building, sorry about that. I was in the poll, so I missed the question. But the point is, building on this premise that you made about the machines, can you help us understand how the technology is ideally suited to address the challenges of the commercial NewSpace industry?
Sure. This is an interesting question, and one that I distilled into what are the challenges of NewSpace or in NewSpace. And for me, there were three key elements which stood out, and everyone has different challenges. But from what we've seen with our customers, there's a key three which I can talk about. As we've seen in the last few years, and with supply chains changing very rapidly and lead times getting ever longer, there is a need for supply chain agility and access to a fast make network at scale. These guys are coming up with ideas, from a paper technical document to a part in the matter of days, and they need a manufacturing process to reflect that. And typically, a lot of machining operations, casting, forming operations might take a suitable or non-suitable length of time. There will be instances where you will use these techniques, and especially with AM hand in hand. But as a first off element, AM is brilliant and on our system of producing these first off parts and then scaling to serial production. And when we talk about serial production, it is all relative over the different markets. Some companies might have a 10 off for serial production. Some might have 100,000 off for serial production. And we've got the ability to provide for both. But ultimately, where we're headed is to supply for the top end of the spectrum. So ensure that we have a large contract manufacturer network to produce repeatable parts across the globe. Something which I've seen very recently as I've learned more about NewSpace is simply NewSpace companies, space companies, designing larger single-piece components for higher payloads. As people are putting more things, let's say, into the air, satellites, communication devices, people per se, there's higher payloads, and that means more thrust and typically means a larger part. And that's where our XC1MZ platform really takes into account these. And that was one of the primary requirements it was driven by from our customers. But there's no point producing big parts if you can't produce repeatability and a good part per se. So we've got the software, as we say, to validate that, and the parameter selection and recipes, golden recipes that are validated for you to complete that. On the right is a very interesting part, which I'll talk about a little bit later. And hopefully you'll be able to see this part with some of the trade shows we'll be attending later in the year, which we'll also talk about. The other thing we see, which again I've alluded to, we can't forget about, is material readiness and material qualification. A lot of these space standards are driven by typical aerospace standards, albeit sometimes with a little bit more flexibility. But from what we see from a lot of our major customers is the need for the qualification of materials and the data to validate that. So not only in-house do we have preset material recipes. For example, the most common one at the moment is the GR-COP42, which everyone is focusing on, the high strength, high conductivity and low creep that we've actually validated or qualified, but they want the internal data for themselves for qualification. So whether that's via traditional techniques of material sampling or part sampling, we've got the ability to produce this. We'll go on and talk a little bit about those few parts later in detail. But for me, those are the main challenges of the commercial NewSpace industry. Happy to have a discussion around if there's any other challenges which people need solutions for.
Absolutely, and to answer that, we have some answers from the poll that we launched. What are the main factors limiting your adoption of AM? And 20% said cost. It's actually very evenly distributed. 30% is lack of knowledge. 20% is challenges with approval and regulations. 9%, now the polls has changed a little bit because it's live, but 8% said designs are comprised by current manufacturing solutions, and 17% by part size. I'm assuming that means that the machines are not large enough, but as we saw, we are addressing that. Again, the polls are live, so now the lack of knowledge is up to 42%. So that's also something that we address constantly and that we are addressing today. And we will talk about a little bit more about this during the webinar and in the questions.
Just to comment on that, David, the lack of knowledge. It's interesting that one's come to the top of the pile, and there's a lot of people doing what we're doing, metal 3D printing on large bed machines, and ultimately that's where we're here to educate and to showcase the technology. So yeah, we're happy to talk through any questions and ensure we get you in front of the hardware and software as well.
Absolutely, and to get more into that, into the possibilities, can you give us some more examples of the successful adoption of Velo3D technology in the production of advanced parts for the space industry?
Of course, yeah. So moving left to right, so the first example is a company called Launcher in the US. So they had their top level requirements is the largest thrust, lowest consumption, lowest cost per kilogram of thrust. And they effectively had a cost versus performance seesaw with some metrics they needed to meet. So the designers went away. They came back with a few designs that met both of these metrics. And via conventional methods, they weren't able to meet the KPIs of cost versus performance in the allotted lead time. So this is where they came to us, and we've had a successful adoption of a flow optimized critical component in Canal 718. So this is the hot end, high strength of things. Another interesting customer that we've been working with, the number 2 part, is this thrust chamber in GR42. It's very, very current, this material. It's one that across a lot of industries are looking at, but it was born out of the space industry. And it's a part optimized for control of fluids and the transfer of heat. Specifically used in high temperature applications where high strength is needed. And it's a very interesting case study, and one which can be, as I said, exploited cross market as well. Number 3 is a launcher orbital propellant tank. So this one is a very interesting part, and you'll see a lot of media and a lot of case studies on the web about this one. So this is a pressure vessel in additive, and you'll see, I don't think you can see my cursor, but the top of the vessel there is actually where we see a 0 degree overhang, which typically in AM you would have to put lots of internal supports. You would increase the weight. You'd effectively use some of that internal volume to build the part, and that's where a launcher sent us what they wanted, what the designers envisaged, and then we were actually able to make it without compromising a lot of those solutions. Other people will use different techniques, but for this application, this worked very well. And in that picture, you can actually see it still on the build plate. If anyone was wondering, that's before we take it off the build plate. And there are some post-machining ops there for interfaces where need be. The other one for that is where we have multifunction parts, consolidation of parts. We talk about it a lot, and it's something we like to look at in terms of cost, and looking at total life cycle cost. If you can integrate all of your performance metrics and KPIs, so thermal, structural, environmental, and reduce the number of parts, you can then start looking at reducing overall costs. So looking at it with a fresh set of eyes at a macro level, let's say. And then simply the one on the right, which is a lot smaller, is a lot bigger than it looks on this screen, is actually built on our 1MZ system. So the whole part takes up much of the build chamber. It's a large scale single piece parts. Typically, a lot of our customers have fabricated these before, with long lead times, with poor quality sometimes, especially as some of these parts are going through thermal and cyclic loading. So, I urge you to come and see this part in a couple of shows, or all over LinkedIn. It's a fairly big part.
And I think to build on that, we have the results of our poll on the types of parts that the audience would like to see implemented in space systems, and the top two are heat exchangers, which is considered kind of a killer application for additive, and we know that with Velo 3D technology, it's particularly effective, and turbo machinery. So those are the two main applications, but also antennas and pressure vessels and manifolds, what you were saying about integrating more parts into consolidating more parts into a single one. So the top two at this time are turbo machinery and heat exchangers. And we can when you look at specifically how the European commercial space market, how has you talked about the center in the new European Center for Velo 3D in Augsburg. How has the European market reacted to Velo 3D technology so far?
Sure. So as you can see, we've had some great success in the US, especially with the space guys. And we've been in the UK, the Nordics, and the rest of Europe now for about 12 months, engaging and doing our first of parts, providing machines with these guys. And the first thing that a lot of people say is, "Wow, we can't believe you can do this. We weren't aware of how different you were to some of the other suppliers in terms of unleashing the shackles of design." And even when we take them to see the machines, the sheer size of the machine does blow people away, alongside the software and validation, because we know that in Europe there is a particular focus on quality and validation, and people are surprised that we have this essentially. Again, most say, "Wow, can't imagine we are seeing a machine with that Z height before," which is always an interesting one of how people fit it into their actual supply chain. And really, as we move forward, the key really is to showcase what we do and provide the understanding on the most challenging design and manufacturing problems. We want to engage very early with our European customers before many have compromised the design, which they might have to do to build on previous systems. So really, it's about engaging with these customers. It's about showcasing to the customers at our Augsburg technical facility, but it's also about collating the customer requirements as well. So, for example, within Europe, we see different requirements in terms of pressure vessels via the PED directive. So we need to ensure that we are providing these for customers. We're new to the business against some established stakeholders, let's say. So we're still learning. So sometimes it's still a learning journey. So it's collating those requirements. In terms of what we're doing in Europe and the shows, we'll talk a little bit about that later, where you can connect with us or connect with us physically.
Yes, we have a good calendar of events that we will be releasing. So what are the next steps for for Velo 3D's expansion in the UK, Nordics, and in Europe?
Good question. So the next steps, we've pulled together a fairly brilliant team around France, UK, Germany, and Italy. So this comprises of a sales and technical team, in which we engage with you very early on in the design and manufacturing phase to understand your inherent technical and commercial woes. So we like to understand what the challenge is and provide a solution. What we're also doing is expanding our CM network within the United Kingdom and the rest of Europe. And essentially, this is to support our global network and ultimately support customers. So we're engaging with companies that are supplying into these industries, aerospace, automotive, energy, that are already meeting stringent requirements, that already might have machining or casting in-house, that know how to make good parts. And these are the companies we want to engage with to expand our network. And we're very open to working with very progressive companies. So this is part of the strategy, as well as I say, engaging at a very technical level and understanding your problems. Just to add, again, we welcome customers to view the end-to-end process, either at the Augsburg facility or at the HQ over in the US in Campbell. You know, we're fairly open book with how we do things to a degree, and we're happy to showcase that and showcase some of the brilliant parts.
Absolutely, and I've seen the machine at many shows, you know, industry shows, but to see it in its context at the Augsburg facility is more impressive. And also, I think people, me in particular, I didn't immediately realize that you launched a machine that had, I think, is it 8 lasers or
lasers?
Yeah, I think that was the first such machine on the market, and you know, this is some really impressive capabilities, and definitely helps to see the machine live, you know, in its natural industrial setting. So thank you so much for this, for all this, and we will get back to you with some questions at the end. Again, the audience, you're free to write your questions in the chat window, and we will answer them at the end of the session. Now, let's get a little bit deeper into the applications of Velo 3D technology in the space segment. As we all know, you know, applications are really what drives additive manufacturing, what drives the business. And here we will talk a little bit more. We will talk with Brian. Can you tell us a little bit more about the most interesting you've seen so far?
Yeah. Thanks, David, for the introduction, and thanks, Will, for giving the overview of where we are at Velo. For me, my background mainly aerospace, and it's kind of like always had that question about the synergy between space and aerospace and how it worked. And I've seen, since being involved more in the space industry, that they're taking on AM more, and they're leading the way on the new techniques, like gone are days of looking into castings, split lines, and kind of like putting of inserts. It's AM's kind of like really focused in space. So we've got I got a case study here showing on screen, which is kind of like mainly focused on the design side and some of the optimization and the techniques that can be used in AM to get that performance improvement that can really reap the benefits. So it shows like a correlation between advanced design software that you can use that's available on the market, and also those advanced manufacturing techniques that we've got at Velo to achieve these kind of designs. So I think we can see on the screen is it's a reaction control system for a spacecraft. It controls the attitude of the satellite or spacecraft. We've got 4 different thrusters, all printing in different directions, and when these thrusters are fired, they change the position and the altitude of the spacecraft. So that's what it does. In simple terms, what's the design of it? What is it? It's a block, and it's got lots of intricate small flow paths with some nozzles attached to it. That's breaking it down into the fundamentals. With intricate flow paths and the coring round to the valves and the valve housing, it's not a simple part to make using those conventional kind of manufacturing methods. So that's where AM really comes to benefit. So what we can see here on the right hand side is a first iteration. It proves that the concept of the part could be created. So what we're doing with Velo is we're trying to we took that Mark 1 version, and then using our design tools and our techniques to produce it and to optimize the performance. The performance gain that we were looking at to try and leverage on this part is weight. When we're taking parts into space, weight counts. So every kilogram of weight that we can remove is definitely a benefit to the system. So the first idea that we had, the first kind of like scope of this, was to take all the internal components and just leave them there, the flow paths, the valve bodies, and create that shell around the surface. So we just had that functional surface, which was kind of like great for performance. We had no bulk material, we had the weight removed, we had the cost removed, and we had the time to kind of like manufacture removed as well. But they needed the structural stiffness to produce them. So that's where we used a external tool to create a lattice structure, which you can see here, that provided the structural stiffness, and that enables a part to be manufactured to the original design requirements. So I don't think we can quite grasp the complexity and how delicate this surface is on the lattice, which would never be able to be made by kind of like conventional methods. It's unique really to AM. So we got around about a 66-67% weight reduction by using this technique, which is unique to AM, and that gives a huge benefit going up into space. The other advantage that we had is the internal geometries. These were complex. They had lots of bends and moved around other geometry to get that optimum size and flow. Normally, these would need support where we have the low angle over the top to close out. But with our technology, we're able to print these with minimum support, still keeping a good surface finish, and still keeping kind of like leak tight on the component. So from that design side, we had that good correlation on three aspects of engineering. We had that structural design to get the lattice structure. We had improvements on our fluid design to get the performance. And we had a part which is kind of like relatively easy to manufacture using AM. So that's the overview of how AM can like really work to optimize and give you that weight improvement on a component which is going up into space.
I think that geometry really gets the point across with all those different size, different thicknesses, different components inside the single part. So what do you see as the main challenges today that you as Velo 3D are addressing, and that need to be addressed to increase? I mean, it would seem like so obvious to just use additive for so many parts in space, but what's still what do you think needs to be addressed to make it even more common?
Okay. So if we look over kind of like social media, LinkedIn and other forms, you see additive is used quite predominantly in space at the moment. Nearly all the commercial space players are using 3D printing in their propulsion systems. Kind of like the use of AM is being leveraged for that optimum performance of our propulsion systems, creating those surfaces that couldn't be created by any other methods. They're creating them faster. We're consolidating parts, reducing the kind of like the BOM part component count. Parts can be iterated faster. Designs can be tested. We can feed back into that testing program, which is great for the people that are using it. But for me, the challenge is for the engineers to see that AM is now competitive for production, for that production environment, not just for development, for that final part that's released to market. We've got increased build capacity and throughput. As we mentioned, we've got 8 kilowatt lasers on our Xc. We're now seeing business cases for parts that are produced in high volumes and at faster rates. So it's the engineer having that vision at the early stage of their design that AM is the way forward for production. When you're starting out your scope of work and you're looking at your part, the challenge is for those engineers to say, how am I going to make this? Am I going to machine it? Am I going to cast it? Am I going to use AM? Am I going to use something else? It's understanding that early stage of the design process, that AM is the way forward.
Yes.
And when you do that, you don't compromise on design or your performance, and you get the manufacturing kind of like bonus as well. So that's kind of like one side, trying to get people to think early on production. The other challenge is to give like the quality engineer or similar role the confidence that the parts are coming off of sound quality. You're getting good parts from the machine. Measurable, reliable data of part quality is successful. It can be successful for implementing those parts to the market. We want data that we can trust. Yeah. So I've got an engineering background, and as an engineer, I want to trust the science, but I want to verify as well. And that's the same as conventional methods, castings and forgings. We all have to do that verification afterwards. So it's little difference here, but it's trying to get that understanding that the AM can be kind of like qualified. So as great as those capabilities are to produce these parts of power by fusion, the complicated structures, we're pushing the boundaries. It means nothing without reliability and that quality of the part. You can have this like free flying, cool kind of like structure with like all the different geometries, but if you've got a critical feature that you can't inspect, you can't view, compromises will be made on the design, and that won't be the way forward. So again, it's that quality side. So we got to give confidence for the parts to come. So I see that quality assurance needs to come along with the journey of additive in the manufacturing side as well. So for me, 2 parts: productionization, we need to get early, and we need to get that quality assurance, that confidence that we've got good parts coming off the machines.
Absolutely. And I mean, and from what we are seeing, now that additive is finally starting to be used, the parts, they do meet the quality requirements in the end, right? It's it's just another process, and sometimes they're even better than traditional made parts. And I'm guessing that from somebody like you with a traditional background, to see these possibilities and have the the fact that you can confirm the quality of the parts is really it opens up so many opportunities, right?
Most definitely, yeah, for sure.
So what would you say, looking specifically at this case, the quad injector, where would you say the benefits of using the Velo 3D technology are most evident compared to other additive manufacturing technologies?
So for looking into the thing, so it hasn't got its own challenges. AM hasn't got like it isn't a free process. So these design tools that we use are producing parts which are kind of like used to be impossible to manufacture using traditional techniques, but they're possible now. So I showed some kind of like complex internal flow paths earlier. that needed to be printed without support, and also the lattice structure with rigidity. These two components can lead themselves to having a recoater clash, a blade clash on the tool. That's kind of when you're printing a part, there's little protrusions, little parts of material raising above the powder bed. You've got a delicate lattice structure, and there's a recoater comes along on conventional or traditional powder bed fusion machines. The recoater can damage these parts. So Velo's got a non-contact recoater technology that kind of like negates this possibility of the recoater contacting with the part that's being printed. So that's kind of one thing that we definitely took advantage of when we're printing the lattice structure, and also when we were printing the geometry, the flow path, the flow channels. That technology also helps us print these closures on the top of the flow channels without any supports. So we can print those flow channels without supports, keeping that surface finish as well. And then the part, I didn't mention the part titanium, so it's susceptible to cracking. So titanium isn't the easiest part to print, especially when you've got bulk and kind of like fine structures within the same part. So we've got a in process kind of stress relief that helps mitigate some printing of our part, and the preprint software that we've at Velo have developed will intelligently identify the areas where we need to have that process applied. There's no user input required, so our software will apply that process or any other process which is needed. Different features need a different approach, and each of these processes has a specific recipe which is predetermined and automatically applied by the process. So you got a great design, but you need to have that manufacturing solution to create the part, really.
So you mentioned before the golden print file. Brian mentioned it, William mentioned it, and I think maybe you also have. But what is it exactly? What is what do you mean by the golden print file? And related to that, what would it take to implement an actual end-use part AM production workflow for space parts production?
Yeah. Okay. So the golden print file is kind of like a term that we've been drawn out of in the US as we've developed the company, but to get that point, it's we need I think we need to go to back to the beginning of that, because repeatable printing is deceptively easy. It's not easy to repeat the same part from machine to machine. It's not easy to produce the same part from site to site. So what we've done at Velo is think about that fleet standardization. So standardizing a fleet of printers which are in a network, and we do this by controlling the parameter sets. So we want to control parameter sets, but also we want to shoot for a known on the material requirements that we're heading towards. So at Velo, we're leading the way, working with the MMPDS. So this is like a source of design allowable material properties for aerospace industry. So we're working with them to get a known that we're working to, and it can be a database for all to view. So I know we're working with one material on that, and I don't know any other companies in the industry that are actually kind of like doing this. So now we know what we're shooting for now. We know what material we kind of properties we can get, and then we got to start controlling the process. So we got to standardize our fleet, standardize the kind of like the Sapphire tool qualification, and we've got a single button calibration. You call it single button. There's a couple more, but not many buttons to press to get the calibration, and then that is driving the consistency of the printers within the fleet. So we've got the material that we're going for. We've got consistent calibration of the printers all the way across the kind of like network. So we're looking at laser alignment, we're looking at beam stability, we're looking at thermal sensors, powder bed quality. So weekly calibrations on these. So we've got the material, we've got the tool. So we then have to get the confidence that our global machines are standardized. We have to get the part qualification, and that's where our golden print file comes in at the back end. So it's a print file that uses the same instructions time after time. It locks everything down. It locks your laser commands. It fits into a kind of like a PLM system. I don't know, Team Center. So we're controlling our material data. We're controlling our fleet, and then we're locking down our standardized processes to get everything into a controlled and measurable data. So yeah, that's good. There's other parts to assure, which is a back end, which helps the golden print file, which I'd love to look at and talk to you about, but I know we're coming to the end of time, so
and we have a lot of
leave a little bit of time open for questions at the end.
Absolutely, and as always, we have a lot of questions, and I also had questions, but the questions from the audience are usually much more on point. So the first one is, I'm sure you get this a lot, but it's good to, I think, clarify it. And I think you both can answer this because Brian, you kind of addressed it. Is how is the support less builds enabled? I don't know if you wanna take this, William or Brian, who wants to address this topic, but feel free to go ahead from a technological or from an application point of view.
Yeah. So okay, go on. I'll take this one, Will. So how's it taken? So there's a few things that we utilize and we use to get our support free kind of like structures. That's the processes and the recipes that we use. These are predefined. These are inbuilt within our system. They are developed by our apps team. And then we've got the control. We have this global control of the processes as well. So they are the ones that help us get the low geometry, the low overhangs, and our non-contact recoater is also a huge benefit to there. So there's a lot of IP behind it. We can go into a little bit more detail post this webinar with others, but it's a combination of the process we use, how we control them, and our non-contact recoater.
Fantastic. And what do you think? What is the most what is common post processing that is used in combination with Velo 3D technology, and more specifically, removing the part from the machine, from the plate? Do you use machining? Do you use you or your clients, do you use HIP, hot isostatic press? What are the most common post processes that you see used in combination with your technology?
For me, it's all of the above, David.
Okay,
we've got that network of contract manufacturers, and I think the way that Will alluded to earlier, we like them to have that all-round engineering experience. So when a customer does have a part printed in the contract manufacturing network, they can go to a place and be secure that they can have a part from a experienced machine shop. They're going to go and have the confidence that this machine shop or these contract manufacturer knows how to heat treat. They know how to manage any traveler packs. They know how to manage a hipping process, and they've got those networks around them already. So for me, there's no one process that's more evident than the other, but they're all controlled at our contract manufacturers, because that's why we select these people to work
just to add to that, some of those we will try and avoid, obviously. So yes, you've got to take this thing off the plate, which sometimes we'll use EDM. But things like HIP and heat treatment, we will try and mitigate by using inbuilt parameter selection. And again, when we think about designing and manufacturing at a higher level, you'll always use machining for interface tolerance, but if you can get away from that interface and the connection of parts, then brilliant. You won't have to machine the end part at that micro level. So just to add.
Absolutely. And so I think this is also, you both can answer this, but I'll ask you first, William. Have you seen, you as Velo 3D or your clients experimented with non-spherical powders? And is it mandatory that the powders are sphericals? And, to extend that, is the powder used in Velo 3D technology the same, diameter and the same type of sphericity that is used in all powder bed fusion technologies?
The first one, that's an interesting question, and one that I don't actually know the answer to. So I'll follow up directly with, was it Mike or Daniel above there? I think the debate about powder size is very interesting, especially when you look at smaller lattices, smaller wall sections. Again, it's something I'm not party to, but we can definitely get the information. But it's an interesting debate. Ultimately, what dictates the ultimate geometry thickness, let's say? Is it beam size? Is it particle size? Is it a combination of both? So you've got to look at every variable, let's say. But yeah, powder's an interesting one. We won't ever dictate that you should go to a certain powder supply, but we will give a powder requirement for the supply chain. And there are some people that we work with that we will put people in contact with, but there are certain contract manufacturers which select their own powder as long as it meets that requirement. Some customers will also have a powder preference, which we're open to as well. But yeah, powder is a very interesting one, and we always get questions, and people are always focused around the whole end-to-end supply chain, and you can't separate that from hardware, software, final part. It all needs to be fully understood and integrated. And the moment the powder's in the machine per se, that's our remit as well. So we need to understand what that powder's doing as it gets researched, as new powder comes in, focusing on batching as well. So we've been through all of that, and we've learned, right, like everyone else. Sometimes got it wrong, sometimes got it right, but we have our own strategy on powder management. Brian, anything to add on powders?
No, I think you covered it. We don't dictate what powder supplier to use from. We validate on one powder, but it's across the board that we can use in our machines.
And before I get back to that, we have another question that's a little bit articulated, so I'll read it, but it's very interesting. So understanding the importance at the early design stages to go from concept to commercial, so not just prototypes, is it equally important to take similar considerations into the raw materials used? And if so, does the design team need to work with material suppliers to provide custom proprietary blends based on end product performance requirements, or is it simply using off-the-shelf materials such as titanium, etc.? We kind of addressed this, but maybe you wanted more specifically reply.
Yeah, kind of address that. I guess distilling that question is, if someone has a specific requirement thermally, structurally, are we developing powders in-house? And a lot of companies will do that. We have a specific focus on market or customer need at the moment. So we have a specific number of materials which we validated through the CM network, and we're working on even more, but it's very much driven by the market and the requirement of the customer. We will never develop a material or powder because everyone else is doing it. We will do it very, very focused. There's only so many of us and so much resource. We need to target that. But if there is a specific requirement, we're open to discuss that and provide other solutions.
And how long does it take to qualify a material generally?
For me, the experience that I've had, it can vary. Depends on whether it's a new material or it's a similar alloy. But we've been able to do it in around about 3 months' time to qualify a new material on one of our systems. But just going back to one of Mike's points, kind of like just growing on a little bit, we have design guidelines that when you have your material, we've got those design guidelines for the different materials that we print. So yeah, you're considering the design requirements at the early stage, depending on the material selected for your the design and the performance that's needed.
Just to add to that, once it's qualified on one Velo machine, it's qualified on all of them, whether it's a Sapphire Xc, 1Z, goes through the whole family.
Okay, fantastic. And so this is really all the time we have for today, but again, I think there are a lot of things that we can go more in depth about, and feel free to reach out. And also, these are, as we mentioned before, these are the events where you will be able to connect. These that you see on your screen are the events that you will be able to connect with the Velo 3D team and see the technologies in person. So in the UK, in Germany, you will also be able to you will also receive the calendar, and please feel free to reach out to the contact links you see on your screen. And thank you very much, everyone, for being with us today. Again, I think there were a lot of very interesting topics that emerged, and we give you the appointment till to next time. Thank you, everyone, for being with us, and thank you for our speakers for the presentation.
Thank you very much for having us.
Thank you all.
See you next time.